Oh, hi, I didn't see you there. This is ridiculous. Well, hi, welcome back. We're back. It's been a while. But we're back, not for very long, probably. You must be wondering, David, why are you wearing these sick glasses? Because they make me look very cool. Of course they do. Well, I hope you enjoy the video. It's a bit of a mess. I was going to make a blooper reel at the end, but I couldn't be bothered. I was too lazy. So instead I made something very entertaining, let's say, at the end. So enjoy the video and, whoopee! Neal's not gonna give me a clap. He gave me a clap. Maddie, where the hell's my clap?
What?
Okay. Thank you. What are you people doing? Anyway, we're gonna do some fun things today. However, I've got to do. I have a pen here. Thanks for writing that. We're gonna do some interesting things today. Don't throw the pen. No. We're going to do some interesting things today. Mr. Blair walked past and he smiled at me and now I feel very uncomfortable. Anyway, we're going to talk about some interesting things today, but I've said that 10 times. But I need to do some logistic things first. The first part will have to do with, I've got a friend, her name is Lucy, she is my best friend, she wants a shout out even though she'll say that it's my show, I can do whatever I want. Hi Lucy. Now,
Happy birthday!
Did you say happy birthday? Oh, I love this. Anyway, today. Yes, she's the inspiration for this show. All of this is her idea. Anyway, today we're going to do some interesting things. Welcome to classification and classification and representation. Hell yeah. If I spell anything wrong, that's not my problem. Now, this is topic 2.2. We finished topic 2.1, which was linear regression. Welcome to 2.2, which is classification and representation. So what does that mean? In other terms, you're going to know this topic by this name, logistic regression. Of course, regression is misleading because this isn't regression at all. Regression. So, this is what we're going to talk today and probably the next few weeks before we move on to neural networks. This is going to be a hard topic, I'm not going to lie to you. This is harder than before, and this is where things really get to step up in terms of math. We're going to talk a bit about probabilities today as well. Yes, Neal?
Does it in any way relate to linear regression?
Not at all.
Okay.
Well, we will compare them both and see what happens when we do. So anyway, first thing is I'm going to introduce you to classification. We talked about this in our first machine learning lesson, which we talked about classification versus regression. There are two different things. There are ones that deal with discrete values, so that means there's a limited number of options. True or false, for example, is classification, while these people better not start making noise while I'm recording here. Anyway. Regression, we talked about having a continuous range of values. For example, height is a regression problem because you got 0.1, 0. Blah, 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 decimal points. Loads of different places that you can be in your height. While classification could be your blood type. You're either A or whatever blood types exist, right? Or you could say true or false. These are classification problems. And we've covered how we can do regression for both polynomial and linear. And so today we're going to talk about classification. And classification can be done using logistic regression. Now, logistic regression, you see, well, it's regression, and I just told you it's a classification problem. This is just a name. It's not actually regression at all. This is misleading. It should be logistic classification, but that's not that fancy. So we're going to call it logistic regression. So, examples of classification problems. Let's think about some. Spam email. Is your email spam or not? Those are two states. Your email is either spam or it's either not spam. There's no in between. No right. Don't question them. And you know, online transactions. Are your online transactions fraudulent or are they not fraudulent? There is no. They're tiny bit fraudulent. You're either breaking the law or not. There's no in between. Or tumors, your tumor could be either malignant or benign. There is no, it's kind of cancerous, but not really. So, okay. Anyone got any other examples, or you want to move on? I don't mind. There are plenty, just doesn't really matter. Anyway, what our goal is. Our goal is very similar to our goal in logistic regression, and we're going to try and predict y values. Our goal is to predict y values. That's our goal. We're going to try and predict y values just as we tried to predict back in linear regression. And how we're going to do this is in a different way, and this is a very different way. There are loads of...
The computer's
Yeah, that's
okay,
what I mean by we predict.
Yeah.
We are not actually going to do this. The computer is going to, right? We're going to talk about how something called a binary class. So we're going to have some value for y. Y is going to be part of some class 0 and 1. Now, what in the ever-loving hell does that mean? Now, y is the thing we want to predict. Before we had y as some number that we were trying to predict before, and now, y, what this means is we're saying that y can either take on the value of 0 or 1. Only 0 or only 1. So we're eventually, y is part of this. So y can equal 0 and 1. Nothing else. That's what that's saying. And we know that this is a classification problem because, well, there's the discrete number of things there are. There's either 0 or 1. Again, there are something called multi-classes. Multi-classes look like this. You have 0, blah, blah, blah. How many classes did you need, right? This is a multi-class. It can either be 1 or 2 or 3 or 4 or 5 or 6. It could be an integer, for example. That's a multi-class. But it doesn't have to just be numbers. It can be letters as well. It can be words. It can be either blah, 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 word, right? Those are multi-class problems. So this is our idea, our intuition for y. Does this make sense, or am I speaking complete gibberish?
Makes sense.
Okay. So, what we're going to we're going to look at this now. We're going to write it here, or write it here. So what we're going to look is, no. Yeah, whatever. So who put the green, yes.
Is the one with the 0, 1, 2, 3, 4, blah, 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 is that still classification?
Yes, because it can only be these values. It cannot be 4.5. It cannot be 4.1.
Like infinity in there, right?
In theory,
Well,
yes,
yeah,
but then it kind of just becomes regression at that point. Don't forget
the dot, dot, dot,
yeah.
means goes kind of like forever.
Consider it more like that. There
Okay.
is only up to 5, right? So, but we can split this up into two things. I don't like this pen. We can split things up into two things. We're going to have our 0, which, what does our 0 and what does our 1 actually represent? Yes,
Like
right.
this?
I'll stick with this till it dies.
Okay.
Then we'll switch to that. Right. So 0 is what we call our negative class. Negative class. You'll see in a second what I mean. Negative does not mean negative number. It's called a negative class for a reason. Negative class, and then we have 1 which is our, well, you guessed it, positive class. Positive class. Now, you might be wondering, well, 0 isn't negative, so how does that make any sense? And, well, of course, 1 is positive. But what we mean is to represent this is in terms of context. Let's imagine you have a cancer, for example, or you might have a cancer and you don't know. You have some tumor, right? This is your tumor. Okay? That's your tumor, right?
Why do we have to imagine that?
Because actually this is one of the main uses that this kind of machine learning is used in. Very, very, very highly used. This is, let's imagine you have some tumor here. And what we mean by negative class is negative class means that you do not have cancer. This is benign, right? This is benign if say your computer spits out a value of 0, which means that it's part of the negative class. It's not part of the positive class. You have not been diagnosed with cancer, right? If this computer, right, we run this through a computer, right, this box, and then it spits out 1, it means that your cancer is positive. That's where it comes from, that it's true. That's why this is called negative, that's why this is called positive. That's the intuition behind it. But don't worry, we just call it a negative and positive class.
So zeros and ones are just because the computer reads like zeros.
We choose 0 and 1s because we could choose any other value, but it's just easier to write 0 and 1, right?
That's fair.
Right. We could, again, this is only for 2. If you had more, then you would have to have 0, 1, 2. And these will no longer be called negative and positive. These will just be called classes, right? So, 0 tends to convey absence, while tends to convey the idea of presence, right? This is why, Mate, 0, the negative class conveys absence, while the positive class conveys presence. Right, okay. So how do we, we're going to try and actually develop an algorithm for this. How are we going to develop an algorithm for this type of machine learning? So I'm going to introduce you to a graph. So if one of you want to move the camera a bit more over there. So let us begin by showing you a graph.
More than was needed, but it's fine.
Yeah.
Yeah, but I want to be in the frame, Ryan. I need the viewers to see me. I'm so beautiful. Now,
That's right.
we're gonna go from some kind of graph, right? And I'm gonna show you how we can graph this sort of data. And it's very simple. You'll get it straight away. You've got your 1 and you've got your 0, right? So 1 can be yes, for example, and no can be no. Now we're going to ask, for example, number. Oh, sorry, we're not gonna write number because we're not fools. We're gonna write number of times Ryan asks a girl out. Now, now, this is a very
We're
simple.
not supposed to only go false here.
No. Let us say that this x represents the number of times. This is x in terms of n. Now, we're going to now graph this kind of information. So, if Ryan asks her out once, she's probably going to say no.
Oh, so this is... But we have no data. Oh, this is...
Ryan,
Okay.
this is theoretical. It may be based on real life circumstances,
Makes sense.
but... Okay, so we can generally graph data to look
Oh, let's go.
like so. Now, I'm being very generous,
That's
of course.
50% odds right there.
Very generous. We have a small data set. Ryan isn't very popular.
That's good.
Now, now, notice how we have our yes class here. This should actually be up there, but never mind. It falls under the yes, this falls under the no. So that means, say that this is 4, right? This n represents 4. After 4 times, this person says no. After, say, 5 times, they say yes. After 6 times, they say yes, 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 yes. Okay? Does that make sense?
This is the same person multiple times?
Irrelevant, Ryan.
Yes, that's harassment.
It doesn't matter, Ryan. You're very
I'm very
pushy,
stubborn.
very pushy, and stubborn. Okay, okay. So I made my life like
This is
maybe.
getting sad.
Okay, now this is good on all, right? So that means that this kind of thing, this, I don't know what I'm going to call this, the Ryan success rate, right? The Ryan rate. The Ryan rate can take. The Ryan rate can then take on 2 values. It can take on the value of either what? It can either take on the value of 1 or 0. Where 0 is the negative class. This is what we consider part of our negative class. So this means that they say no. But part of our positive class is this, because now the value of this is 1. There's no in between. There is no here. There is no saying maybe, okay?
I mean, technically there is.
Shut up! Irrelevant. For our purposes, right?
In this case,
Ryan is either the most desirable person in
Ryan
the world
is
or the least.
nothing.
Okay? But notice how there is no maybe. Sorry, that shouldn't exist there. There is no maybe, there is no in between. There is only yes or there is only no. I mean, you could in theory have a third class that is maybe, but then we would have to graph it in 3 dimensions.
No, you can draw one conclusion. Ryan is an idealist. So,
I did.
so when she says maybe, Ryan says no.
Okay, I overcomplicated this. I had like tumors and malignancy in this, but that seemed kind of depressing, so...
We made it a little more happy. Well,
Okay, but now how are we going to fit a line to this data? How are we going to fit some kind of data line to this? So how we're going to do it, we can look at it, what if we were to do it using, well, you guys might be thinking, well, this looks, it doesn't look that linear, but it could be if we... Did you try to drink hand sanitizer?
Couldn't have been better.
Brian, we need energy.
I hate all of you. Okay. Now, we can try and fit, this looks it doesn't look that linear, but sure, like it could make kind of sense to say that, right? Now, you're not that far off. And you know, what we're going to try and do is we're fitting this curve. What's the formula of this curve? Well, it should be h theta of x is going to be theta transpose x, right? You should know that from last lesson. So notice that this is this one. Of course, Ryan doesn't remember. So this is this. Now, who could spot any problems with this? Right?
Why would you ask a girl out if she has already said yes?
That's a fair
Do you people want me to put cancer sizes here? Is that what you want?
Wait, no, but it doesn't specify one person.
Okay, it doesn't matter. I'm fitting this line to some set of data. It doesn't matter if the data here is number of times Ryan asks a girl out or the number of times I build a nuclear bomb in my shed.
FBI, open up!
It doesn't matter. Just look at the data and tell me the problem. Now, firstly, I haven't told you introduce this idea of a threshold, right? At what point does Ryan's insistent asking actually work? Well, it seems to be about this, right? This is what we're going to call a threshold. This is some threshold.
Ah, yes.
Threshold. So notice that after this threshold, Ryan's progress seems to be actually working rather than before. So we're going to say that this threshold exists, right? We're going to say that this threshold here exists when h theta of x is greater or equal to 0.5. So that should make sense.
Okay.
Not 0.5. It's at 0.5. Sorry. Yeah, that is true. Sorry.
What?
Yeah, that was
That is
seemed right.
That is true. Sorry. Now, so what I'm saying here is when this isn't 0.5 here, it's 0.5 here. Notice how this is some equation h theta of x, right?
Okay.
This function, we could just write it as f of x, it doesn't matter. This f of x, if f of x is greater or equal to 0.5, which is above this line,
Yeah.
above this line, then he seems to be successful. If it's below this line, he seems to be not successful. That's what the idea is, right?
Okay.
That. Shut up, Brian. Now, that's our idea. So what we can do is we can build a small algorithm that works. Yes, Neil.
Is that dot supposed to lie on the line?
Yes, it does.
Okay.
I'm a bad drawer. I'm a lazy ass. Don't stop criticizing me. I take enough flack from you people.
Really? That does sound
Yeah, the
Is it
scale
that
is
hard to draw?
the scale is.
Neil, I'm an incompetent fool. Okay, I don't think I need any more. Whatever it's called. Now, anyway. We're going to predict. So we're going back from over here all the way over here because I'm too lazy to rub things away. We are going to say predict that h theta of x, right? If it is greater or equal to 0.5, we're going to predict that y equals 1, right? We're going to make this prediction. If h theta, yes.
Why do we say equal as well? Because it's technically in between, so.
Oh, we just tend to
Is it
think
like
of
round?
if it's to this side of the boundary, then it's greater or equal to, because if it falls on this boundary, we're just going to say rounding up.
Okay, yeah.
That's what we're doing. We round up in computer science. So we're going to have h theta of x. If that is less than 0.5, what are we going to predict?
Should it be less or equal to?
Or just less than? Because we're not going to, we're rounding up.
Okay.
We're going to predict 0, yes. We're going to predict that y equals 0.
Yes.
So that means if h theta of x here, right? This is below 0.5, right? So that means we're going to predict no. Ryan's attempts are not successful, right? So that means, how can we rewrite this in an interesting way? Now, you guys are familiar with piecewise functions, or should be familiar. Ryan, do you know what a piecewise function is?
No.
This is why you don't do HL math. No, it's a very easy function that can be defined in terms of multiple things. So it looks like that, and we say that it's going to be,
Have you guys done this in nature?
you should have done this in MYP5.
What? What is it?
Y equals 1,
Just using a fancy name.
h theta of x.
Yeah, probably.
Yeah.
You've seen this before. All I'm saying is I've defined this as one big function. This function h theta of x is this function,
yeah,
right?
yeah.
Just writing it, yeah.
Yeah, yeah. So,
do this
this is
every
called a piecewise
Yeah,
function.
literally, yeah.
Piecewise function, right?
Okay, is that what it's called?
Yeah, piecewise function.
Piece
Now-
wise.
For this example, linear regression seems to be, doing a pretty good job at it. But what happens if Ryan tries again, right? Now, let's imagine Ryan. I have to read. I wrote this stuff out. But you guys are finding what the goals are and stuff, right?
Yeah.
Why do we make it linear again? Is there a reason?
I'll show you why we're putting it linear and then showing you why it doesn't work. Now I'm about to show you why it doesn't work. So let's say Ryan tries again, this time 1,000 times. I don't know, some arbitrary number of times, right? And they say yes.
Damn.
Because at this point, Ryan is holding her hostage.
They have,
No.
they have children now.
The first 4 times I got told no, the rest.
Yeah,
I
yes.
did. I did.
Okay, now what we're going to do is going to rerun gradient descent. Okay?
Okay.
We're going to have to rerun it and build, because when we add new data, this line is no longer going to stay here. It's going to become a new line, right? Because it's going to come back. So if we rerun it, it's going to look probably something like this.
Oh, wait a minute.
Oh.
I mean, if it's 1,000, well, we understand the concept, but it would look like crazy if it was like
Yeah,
1,000.
yeah.
Yeah.
Something like that, right? That's our new HD.
Wait.
Yeah.
So wait.
Because that's moved to the side. Because linear regression has now seen that this point is there. It's
So
going
that
to
one
move
at the
it
end is
more.
like the 1,000th point.
Okay,
Yeah.
okay, wait.
So this is new.
Wait. What does the line represent?
This one is this line with the new one.
Yeah.
Once you've added this point of data.
What do they represent?
This line is what we call our, this is our, kind of like our decision boundary. So this is going to tell us the threshold, where the threshold is. So at this point we're going to say, well, the threshold is now moved to here. Notice how the threshold is, if you keep this threshold the same, if x is that, your decision boundary will be here.
Wait a minute. But it's not actually.
I know, that's the problem. Notice how if it's here, then we're saying, well, if it's 0, well, if you're, here, we're going to say that these attempts shouldn't have worked, but they did. So this is an inaccurate model. Notice how it doesn't predict correctly. Because it says, well, this shouldn't happen, and says that this should happen. Well, this should have happened as well, so our decision boundary shouldn't have moved.
That's why linear is flawed.
This is why linear is flawed. It says here, I have in my notes, is by adding a new point of data, linear regression no longer works correctly. Because it's forced to rerun again, and when it reruns again, it says, well, this data no longer fits this, so it's not going to work anymore.
Can't they make a better line though?
It doesn't matter. Lines will not work for us.
Okay.
So I'm going to try and introduce to you this kind of idea that first I'm going to have to add boundaries to my function, to this h of x function. Don't think of it linear, just think of it as an arbitrary function, right? We're going to add some kind of boundaries to this function. H theta of x, right, is going to lie between 0 and 1, including 0. It's going to lie between them. I'm creating these conditions for an easy reason. Because we're not, remember that our y is defined in terms of 0 and 1. The max, the min is 0, the max is 1. There is no in between. Why would I want anything bigger than 1 and anything less than 0? We're going to have it, it's going to exist in between there, right?
Yeah.
So if it exists in between there, I've actually created an algorithm right away. This is not a regression algorithm, this is a classification algorithm. So I'm going to introduce you to the new hypothesis. Remember our old hypothesis function that you guys keep forgetting is this. H theta transpose of x. Again, we talked about the long expanded version. This is just the short. This is the old. This is for linear. Linear slash polynomial. Of course, you could try and fit a polynomial to this. You get the same problems as linear.
Really?
Now, yes, you get the same problems as linear because you cannot increase the number of parameters that you have. So you can end up with some crazy looking functions that don't fit to what you want. So I'm going to introduce you to the new hypothesis. So the new hypothesis is this. I want you to learn this off by heart, and you're going to know this function very well. Mr. Saduma actually talked about it in math today. So let me introduce it to you. H theta of x is going to be equal to some function g of z. Now, of course, that's like, what the hell does that mean? Neal, what the hell are you doing?
He's actually making graphs.
Okay, good. Make graphs.
It's good.
Okay, make graphs. So what does this function mean, right? Why is this hypothesis even valid? This is like a very shortened version. I'll show you the proper full one. You've got g of z. What is g of z?
Is this to do with like 3D? And
You see.
this X, right?
You'll see in a second. G of z is a function written like this. 1 over 1 plus e to the minus z. This is g of z. This is logistic regression.
Can you change the G to J?
No, I'm not going to give you JZ, just for the sake. We're sticking with GZ. His Chinese rip-off cousin. Now, this function, we can rewrite it in another way in terms of theta transpose x, because we want it in that term. Z is kind of arbitrary, it doesn't mean much to us.
If we make zx, does it work just fine?
If you graph it, if you want to graph it, put an x there and you'll see the function. But I'll graph it for you by hand, because you need to know what it looks like. So if let's rewrite this in terms of this, and you'll see the final function that I'm going to show you that you need to learn. It's g of, not g of z, it's g of theta transpose t, right? And that's going to be equal to, well, notice that all I'm going to do is replace z with theta transpose t. Damn it. It's going to turn 1 plus e to the negative theta transpose x. That is it. Now what does that look like, right? If Neal, you can try graph this in Desmos and you should find a function. Okay, good. So what does it look like? It's going to look like this. So we're going to have our axis like so. Whoop-om, right, like that. It's going to pass through 0.5. And if it's going to pass through 0.5, it's going to look like this. Now, what is the limit of this function?
It's negative.
Hmm? What do you mean?
What?
That's negative.
Yeah, but it's so.
Yeah, that's
It's
fine.
still 0 and 1.
Yeah.
You see in a second. We're not done yet. We don't know what this means. Now, what is the top, Neal, if you look on your graph, what's the biggest value that this becomes? What does it tend to?
1.
1. And what's the minimum that it tends to? 0. Like so. 1 and 0. Now notice here that this, if you look and try and draw this onto your data, it fits much better to your data. But it's not just it. But how are we going to predict using this? How are we going to predict using this, right? If something is, actually let's not skip too far ahead. Just know that this function exists, and this has a name. This is called a sigmoid. And my understanding of why it's called a sigmoid is because this, which you will use in integration, is a stretched out sigma, which I'm going to call a sigmoid. Anyway, now that we have this function, which is all going to be equal to h theta of x, by the way, this is all equal to that. So that is our logistic regression hypothesis function, which is in your data booklets. What h theta of x actually does, what this thing does, is it's going to, if we turn the camera a smidge.
It could see.
Yeah, but it needs me in this photo, right? We're gonna, what this does is, all of this does is actually calculate the probability that y equals 1. So this calculates probability, that y equals 1. So I'm going to show you some actual notation, right? So what do you mean by calculate the probability that y equals 1? Let's say that Ryan tries this number of times, right? And if I see this number of times, I don't know, maybe this is 7 times, right? Ryan tries 7 times. And if we go up to the actual curve, to the actually this isn't even coming on camera. Anyway, and let's say you have some point of data here, right? On point data, and you go up to here. Notice where that thing is. It's over here. Some data is going to be on this curve over here. 1 second, right? And then go up to here, it's 1. So that means if this happens at this point, the probability of it being 1 is 1, which is 100%. That's what this is. This is a probability curve. Yes?
In any cases where you have like 4 point something, like
yes, you can have numbers. It can be anything here on this, because I just throw discrete values on that, but this can be something else. Right. So this is going to calculate the probability that y equals 1. And I'm going to introduce you to the notation we use to represent this. It's going to look fancy, and HL students will learn this in DB2, but I'm going to show you it now so that you guys understand. It's very simple. It's that P, so that's the probability, right, that y equals 1, and then a line there, x, semicolon, theta, this. What does that mean? That means that the probability that y equals 1, x parameterized by theta. And what I mean by that is, again, you should get this should be fine, that the probability that y equals 1. And x parameterized by theta is that theta is changing x. Remember we talked about how this theta affects, these are our weights, these are our parameters. We want to find our thetas. Even in logistic regression, all we're doing is finding our thetas. So this is just telling, based on theta, x, how will that influence y, right? And in essence, we just write this. And here's some rules you have to realize, is that this plus this, y equals 0, x parameterized by theta. What's that? What's the value of this? And apparent from this graph, you should figure it out that it's going to always be 1. Because, well, the probability, right? If I put probability here, it's going to be, say, like 0.75, right? This 0.75 is 75%.
Yeah.
So that means that the probability that it is y equals 1 is 0.75. And the probability that it's 0 is 0.25, right? Obviously, that's the chance. And that's always going to be equal to 1. That's what that means. That the probability that y equals 1 plus the probability that y equals 0 is 1. Because you can't have either more you can't have higher than 100% probability or lower than 100%. So this can always be true. And this is kind of useful for math, but we are not going to use it that often. Just notice that what this means is the probability that y equals something, x parameterized by theta. Does that make any sense? Now notice here. Notice that, look at this point of data is on this. It doesn't matter, it should be just arbitrary, right? And we go up to our sigmoid function, and it's over here. And we draw to our y-axis is over here. Is this value less than 0.5? Yes. That means what are we going to predict? We're going to predict that y equals 0, right? So if we're going to look, we can fit our data like this. We're going to, again, do Ryan's attempt at success, right? We're going to have some data here. Notice how all of these are less, if we go to our y-axis, are all going to be less.
But would that still be attempt 1?
What do you mean? Yes, that would still be attempt 1.
Even though it's on like a...
Yeah.
Okay.
This is just a graph of sorts. We don't
It's
really...
not actually like... Okay.
We don't really... We're just considering it like this. Don't worry about it. Okay? So notice how if some value is greater than 0.5, then, or greater or equal to, it's going to say that y is 1. If it's not, it's going to be y is 0. So, that is our thing, and I'm going to show you the decision boundary. We may need to wipe some stuff away. And, okay. We have 15-ish minutes. I'm going to end off with decision boundaries and some cool, and then probably the math summary of this, because you might need some, because there's a lot of math that we covered today. And I fear that it's kind of abstract to get straight away, and I don't want to be like... I just don't want to like tell you and just expect you to know.
I mean, I kind of understand, but I don't understand how the computer's gonna...
No, okay, that's a story for
yeah.
for Thursday. Don't worry about it. That's Thursday's lesson. But we're gonna draw a really big. We don't need it that big. We just need it like that, right? This is some graph here, and this is some value. This is some value x1, and this is the value x2. Not y. Notice that this isn't y, and this is x1. Now, this is a kind of a concept known as clustering a bit. So let's imagine you have some circles, right? These circles represent something. And then these x's represent something else. So, because it's easier to explain, let's imagine that this is going to be size, or it could be, because these are actually two features, it can be two different things. You have some feature, right? So if your feature of x1 has some value here and has some value over here, right? It's going to come up to here, right? So it's most likely going to fall in the x category, right? So notice how this probably, you could see that, there's some boundary here between the x's and this. And this is where we draw something known as our decision boundary. And our decision boundary looks a bit like that. So anything onto the left of this curve, on this line, is in the circle group. Everything to the right of this curve, of this line, is in the x group. Okay. So notice how all of these, what is the value of y for these? Y equals 1. What is the value of y for all of these?
Did you ever swap that? On the...
Yeah, you can swap. It doesn't matter. Okay. Yeah. You can end up with swapped, and I'll show you in a few minutes. I'll show you some very funky looking decision boundaries that you can have. But for our purposes, this is where y equals 0, and this is where y equals 1. Notice how it looks like this. And this is after we've applied our sigmoid function, by the way. We've applied our sigmoid function, and you're left with this kind of data split like this. So, let us actually find the equation of this line. How are we going to find the equation of this line? Well, we're going to end up, let's imagine we have some theta. Remember, our theta is a matrix. We're going to talk about it in terms of matrices. And it's going to have the value minus 3, 1, 1, for example. right? That means that theta 0, theta 1, and theta 2, right? For that. So, what we're actually going to do, and let's imagine the equation is like it looks like this. It looks like theta 0 plus theta 1 x1 plus theta 2 x2, right? Let's imagine this is our equation of our parameters. It can look in lots of ways, but don't worry about it. So h theta of x,
x0 always equals 1, right?
x0 is always 1.
Okay, yeah.
Always.
Okay.
Okay, so let's imagine we're going to have our h theta of x, and that's going to be equal to g of, remember we talked about it's g of z, and z is this. This is our z, so we're going to shove this thing in, plus theta 1 x1, theta 2 x2. Right? We shove this thing in, slap it inside, and we're going to be left with this, right? And let's say, remember, we know the value of theta 0, we know the value of theta 1, and we know the value of theta 2. So we've already done all of our algorithms to find the theta values. We know the theta values. We just want to find this boundary, right? And to find the gradient of this boundary, let's shove in all of the values for our theta 0, theta 1, theta 2. Well, notice how theta 0 is negative 3, so negative 3 plus x1 plus x2, because 1, 1, right? Like so. So this is going to be, again, all of this is equal to this. Theta transpose of x is all going to be equal to that. So, if we want to predict that y equals 1, remember we said that we're going to have our h of the x is going to be greater than 0.5. But to predict that y is 1, we're going to assume that the value of all of this is going to be greater or equal to 0. Because, well, if you took a look on your sigmoid curve, notice how this value, because actually the x-axis would be here. I'll draw a small sigmoid here, right? Like so. Right? Notice how everything to the right of this is greater than 0. If everything to the left is less than 0, right? This is greater than, less than 0. So we're going to, Mane, are you okay?
Yeah.
Are you sure? I know, this part is very mathy. Don't get me wrong. But it can do some really funky things once we get deeper into it. Now, Ryan, be quiet. Now, we're going to predict that all of this is greater or equal to 0. So we're going to say that 8 plus x1 plus x2 is greater or equal to 0. Let's solve this equation. And you guys should, this inequality, I mean, you guys should know that x1 greater than 3.
Yeah.
And how do I graph this? Well, I'm going to graph that by saying that it's going to be equal to 3. And notice that this is the equation of a straight line. This is the equation of that line. Now notice that what if we want to find that predict that y is equal to 0? Well, if y is equal to 0, we're going to predict the opposite. We're going to say that minus 3 plus x1 plus x2 is going to be less than 0. And if we do that and solve it again, we're still going to plot this curve, but notice that less than 3. Right? In essence, what this is telling you, right, is if the value of your, what it's telling you, right, is on this curve, right, if the value of your, if your value of your x1 plus your x2 is less than 3, you fall in this group. If your value is greater than 3, you fall in this group. That's all that's all the decision boundary is telling you. Yes, right.
And on the line, we still say 1?
On this line,
Yeah.
we're going to still say 1, yes. We notice that the
Wait.
condition is greater or equal to 0.
So actually it's x1 and y1, right?
Yes, that is x1, that is y1.
Yeah.
And no, this is x1, this is x2.
Oh,
there are multiple features.
Why?
This has got two features.
The graph is
Yeah,
x, okay.
yeah. This isn't a graph of y, this is a graph of x. And then y just happens to be, well, these will all fall into y1, and this will all fall into the y0 category. Okay?
Yeah.
So, again, we have the same thing. We've talked about decision boundaries, and I want to show you some. Let's see. Okay, we have a bit of time. The decision boundary is a property of your hypothesis function. It is a property of the function that I showed you of your sigmoid function. There exists that. That is a property of your sigmoid function. I had another example, but I don't think I'll waste time with it. It's a general idea, except that you have it like that, and then that on that side is that on that side is that. Same idea, exactly the same. Now, the funny thing is you can have things that are non-linear though. You do not need this. So let us look at some very funky looking decision boundaries before we head off. I'm going to assume that you're paying attention, right? Because do you want to test on Thursday? On this? Okay.
What do you even test on this?
I'll get you to solve these equations
I guess you could do that.
without your data.
But that would just be pure math then.
Hey, who said computer science was nothing but math, right? We're gonna have this axes, yeah. We're gonna have these plot, and then we're gonna have our x's around it. Now,
Oh, it's in a circle this time.
aha, we can't have a linear decision boundary here. What are we gonna do? Well, you're going to have a decision boundary. Looks like that.
That's the circle.
Nice.
Right.
Wait, is that how missiles work?
To my understanding, no. But the idea is really, I mean, you could build a machine learning program that recognizes missiles and then is able to do that, yeah. But to my understanding, no. But this idea is essentially, if it falls outside of this curve. Yes, Neal? What is it?
No.
Okay, so let us rewrite. I'm going to do the same thing I did for the other one before we end off. We're going to have our h theta of x, right? It's going to be equal to g of theta 0 plus theta 1, x1 plus theta 2, x2 plus theta 3, x1 squared plus theta 4, x2 squared. Like so. Right. And I'm going to give it some parameter values. So theta is going to take on the value of minus 1, 0, 0, 1, 1. Okay? And I chose these values for a reason, because if you actually use these values and find out that you plug these values in, you're going to get the equation of a circle. And I'm going to show you all of that. So if we take all these values, substitute our thetas into our equation, what we're going to get spit out, we're going to get minus 1 plus x21 plus x22, right? And that is, notice that that is the equation of a circle, radius negative of radius 1. So we're going to have some, remember, if we want to predict that y is going to be 1, we're going to say that this is greater or equal to 0. x22 is greater or equal to 0, or plus negative 1. Move negative 1 to the other side, x squared 1 plus x22 greater or equal to 1. Plotting the equation version of that, will give you this circle. Yes, Neal?
How did you get theta? Can you explain how to get theta again?
Well, I haven't explained to you how to get theta. That is what Thursday's lesson will be about.
Okay.
This is going to, in essence,
We got it.
this is in essence going to, I'm telling you that these are the true values for theta, because only these values for theta will spit out a circle decision boundary. Our goal of machine learning on these kind of data sets is to look for the decision boundary, because if we know the decision boundary, that means, let's say we have some new set of data here, it's most likely going to fall in the X class. If it's in some decision boundary here, it's going to most likely fall in the O class. Yes, Maria?
So the what was it? The boundary
Yes.
is an equation.
Yes, the boundary is an equation. It can be linear, or you could be circle, it could be anything. Anything, literally anything. And that is determined by this function that we will talk about how we reach that function, and then we'll talk about how we reach these status. But all today you need to understand is there exists a function called a sigmoid function that has the properties that if it's a probability curve, that if the probability is greater than 0.5, we're going to assume it's 1. If it's less than that, we're going to assume it's 0. And that is very useful in predicting how many times Ryan is going to get a restraining order. Now, thank you very much. And that's the lesson.
We clap at the end.
Yeah, we clap at the end. Hell yeah, you do.
Oh shit, here we go again.